Welcome back everyone, my name is Pedram and this is where we do advanced time series analysis, deep forecasting. Alright, let's wrap up the theory section of our module number 5, machine learning for time series forecasting. In part 1, we talked about fundamentals of machine learning for time series forecasting. In part 2, we talked about decision tree-based models. We looked into the intuition behind these models and we discussed why these models are different from each other and how they are different from each other. Then we talked about a very simple example, which was a univariate time series forecasting using airline passenger data, and we tried to apply a simple decision tree or random forest model to that. And we raised the concern about the challenges when we are doing a machine learning model and applying it to a time series dataset. And then here in this part 3, we will talk about the challenges in time series specifically when it comes to using a machine learning models. So Module 5, Part 3, Challenges in Time Series Machine Learning. In this short lecture video, I will talk about some separate topics that these are challenges when we're dealing with the time series machine learning task. I'm going to start with the non-stationary data and we see how machine learning models are able or not able to handle that. Then we move on to the cross-validation and see what is the right way of doing time series cross-validation. And we finally conclude this lecture video by going over bootstrapping. We know that we cannot do regular bootstrapping, which is sampling with replacement, basically shuffling the time series data. We have to make sure that we're doing block bootstrap. We're saving the notion of time intervals in between the observations. So let's dive into all these details. I want to start with the notion of stationarity, right? So what is stationary versus non-stationary? Hopefully you remember from our module 1 when we covered the time series basics, what is a stationary time series, what is not a stationary. So if you don't remember, here's a quick recap. So in a stationary time series, the statistical properties do not depend on time, right? So look at this example, the green one, this green time series. This is a sequence of data which is obviously stationary. The average is constant. We talked about these things in very details in module 1, so feel free to go back to that video if you need a refresher. The variance is constant, and basically, so this is our stationary. We also discussed the notion of weak stationary versus a strong stationary, but here let's keep things simple. And for example, if there's trend in the data, obviously this is not going to be stationary because the average is going to be increasing. This is not stationary because the variance is increasing or decreasing. You see the variance is increasing and it's decreasing, right? And this one is not stationary because the covariance depends on time. So in general, we said that if there's a trend and seasonality in the data, that's a clear sign that your dataset is not stationary. So if the dataset is not stationary, what's the problem with that, right? We remembered from the econometric section of the course, different models handle it differently. So for example, if I have a, airline passenger data, if it is well behaved, something like that, right? There's a clear trend, there's clear seasonality. ETS model handled that trend and seasonality specifically. So I'm not concerned about that the data is not stationary there. The same story with ARIMA, right? ARIMA differenced the data by the I component and then turned it into a stationary, then applied AR and MA components and then solved the problem. What about machine learning? Can machine learning internally handle the problem of non-stationarity? Let's look into the details. That totally depends on if our non-stationary data set, is it well behaved or not, right? So what is an example? So for example, our very own airline passenger data set, as you can see it here, down here, this is an example of well-behaved non-stationary data. It shows a clear upward trend and seasonal patterns. So this is non-stationary, but predictable. It has a predictable structure. In that case, I would say machine learning models, we don't need to necessarily transform the data from non-stationary to stationary as long as your feature engineering is deep enough, right? So how did econometric handles it? ETS models handle trend and seasonality directly. ARIMA difference the data, made it stationary, and then applied the AR and MA components. Machine learning, we can do it by doing correct feature engineering, right? So we can include enough, again, I'm emphasizing enough number of flags, and then maybe some other time-based features. So with that, most probably the model is going to capture that clear trend and seasonality. If not, we need to move on and make the data set stationary first. What if our non-stationary dataset is complex? Then can we go ahead and again difference the data or use some simple feature engineering and apply machine learning model to that complex non-stationary data? The answer is, well, we can try, but we should go for more complex feature engineering or even more complex models themselves. So what is an example? The example is any kind of financial stock price, right? So Apple stock price, this is the Apple stock price. Obviously, it's not a stationary simply because it's driven by external or random factors, right? And as you can see, the average is not constant, the variance is changing, and etc., etc. So this sequence of data fundamentally have some randomness in it, and that's because of the market structure, news, events. These are some random events that basically we cannot predict them, right? And those time series may have sudden jumps, volatility, and even regime shifts, right? So for example, a company when it's in its growth phase, the stock price might behave completely different from when the company is in its maturity phase, right? So what are the challenges? The challenge is that now here a simple differencing or basically trend seasonality modeling may not be enough, right? We need more advanced techniques. What are those techniques? When it comes to feature engineering, we have to do additional feature engineering. We need to look at the volatility measures. We need to look at external economic indicators as some extra features. So that's one thing. And then we can also think about regime switching models, to capture structural breaks, right? Maybe we need to use spline models to just split the data into two sections and model each part differently, right? And then sometimes the answer is to just simply use more complex model, right? Like the deep learning or more advanced machine learning models with more sophisticated patterns. Okay, so what are cross-validation techniques in time series? Remember, with time series, especially if it is a stationary, we simply cannot shuffle the data because time series are autocorrelated and they are not IID, right? Even if the data is stationary, there's still some time dependencies, like in ARIMA models, right? After all, it's not quite a white noise, so we need to use different cross-validation methods, right? And so basically the main reason is that we cannot shuffle the data, and even if you can shuffle the data, there's still some time dependencies. And we need to make sure that we have to avoid data leakage, right? So we're going to talk about data leakage in the next slide, but in a nutshell, data leakage happens when the training sets and test sets are sharing some information, right? So imagine this is our K-fold cross-validation. We need to make sure that there is no data leakage between train set and test set, right? In these points. So there are ways to fix that when it comes to time series, right? So based on these requirements, we're going to deal with different cross-validation methods for time series, but the three most commonly used ones, or the ones that work in practice, are these ones, right? The first one is Purged K-fold cross-validation. The second one, which most probably you have seen this before, is Walkforward rolling or expanding windows cross-validation. And the third one is Combinatorial purge cross-validation, this is actually a quite interesting one, which was developed by Marcus Lopez do Prado, which he talks about this method in his fantastic books, which is called Advances in Financial Machine Learning. Okay, so let's look into the first one. Purged K-fold cross-validation. So the idea of Purged K-fold cross-validation is all about data leakage, right? And as I said earlier, leakage takes place when the training set contains information that also appears in the test set, right? Because this is time series, right? After all, T and T plus 1 are serially correlated. And if you tend to put them in different buckets, then these buckets have some data leakage into each other, right? So this is not surprising at all. And what's the problem of leakage? The problem is that leakage will enhance your model performance. So you're going to get fake model performance, right? So what is the solution? And actually, let me show you this one. So imagine this is your train set, and obviously you have a non-stationary data set here, the time series here. So let's say we have train set, test set, and again, another train set, and we can go ahead and multiply it into multiple train and test splits, right? And as you can see, there is this overlap. So what is the solution? The solution is what Marcus Lopez do Prado calls purging and embargoing in his book Advances in Financial Machine Learning, right? So, and the idea is quite simple. So purging is, so if you pay attention to this green shaded areas. So purging happens basically to reduce the data leakage. We are going to remove observations or purge observations from the train set that have overlap with the test set. Remember, this is our, let me use the right marker. This is our train, this is test, this is train again, right? So the idea is that remove these observations that overlap between train and test. So we're going to have cushions. Let me use the right color. Okay, we're going to have an extra cushion here, an extra cushion here, right? So this is the idea of purging. So what is embargoing? And the embargoing is, so we are going to add an extra buffer or extra cushion right after the test set and right before the train set to make sure that these serial correlations are avoided or minimized, right? So this is the idea of purging and embargoing. Now, if we apply this purging and embargoing things to K-fold cross-validation, this technique is called Purged K-fold cross-validation. Basically, by adding purging and embargoing whenever we produce a train test split in our K-fold cross-validation. Let's say I have my own 5-fold cross-validation, right? So 1, 2, 3, 4, 5. And every single time that you see a train test split, you're going to apply purge and embargoing. So for example, here right after test, we're going to have, here we are going to have purge, embargo, and then we are going to have purge, purge, embargo. We're going to have purge, purge, embargo, and etc. Right? And we're going to apply this and then calculate the performance on the test set in each fold. And just like any other K-fold cross-validation, we are going to combine these performances. For example, take the average if it is, let's say, RMSE, and then call it the cross-validation performance metric. All right. The second cross-validation techniques for time series is walk-forward, right? We can have two forms of walk-forward cross-validation. One is using rolling windows on the right, and the other one is using expanding windows. So starting from the walk-forward cross-validation rolling windows or sliding windows, we can say in this method, the data is split into series of overlapping windows, and as you can see, these ones have overlap, right? Where each window represents a train set and the following window represents the corresponding test set, right? So we have our train set and the following one is going to be our test set. So the size of the test set is fixed. The size of the rolling window, it can be fixed, it can be different, right? So these sizes can change. Well, we are going to use this sliding walk forward cross validation when the data set, when we have a large number of observations, right? When we have large number of observations and to avoid the structural changes over time series, we would be using rolling windows, right? Because, especially when it comes to stock market, Apple 10 years ago is different from Apple today, right? So it's not useful to use, by useful, it's not quite practical to use information from 10 years ago necessarily when you want to study what's the behavior of Apple stock price today, right? So maybe you should use rolling windows of 1 year or 6 months, right? So that's the idea of walk forward rolling windows cross validation. And for expanding, that's basically similar to a sliding window, but the training set is expanded with each iteration, right? So as you can see, this is your train set first, and we're going to expand it, and etc. And we keep the size of the test sets similar. So this method is used when you have limited time series available, right? So if you have a small data set, there is no structural change in the time series, you can apply walk forward. But regardless if you use rolling or expanding, there are some advantages and disadvantages for this cross-validation technique. So let's talk about the advantages. So maybe the biggest advantage of walk forward cross-validation is it has a clear historical interpretation, right? Basically, especially if you're doing backtesting, it is consistent with the historical backtesting and paper trading, right? So you see, for example, in expanding window, you see from day 1 to day T, and you observe one full path of the data, and this is basically your historical data, right? And so we can say that history is acting some sort of like a filtration, and the test set is completely out of sample, right? So here at each fold, at each cross-validation fold, we're seeing test set is completely separate from the train. And because test set is always coming after the train set, we don't need to do any kind of embargoing, but we need to do some purging, right? So we need to do some purging to make sure that there is no data leakage, okay? So these are the advantages. What is the disadvantage? So the disadvantage, and again, maybe the biggest one, is that it's what's called a single scenario test. It's basically show you the historical path. It's going to generate one path from day one to day t. And usually this is your historical data, and when it comes to trading, the model can overfit. The model can overfit if there's only one path, right? So the solution is what we call combinatorial cross-validation. That's basically the idea of combinatorial cross-validation, is to generate multiple of these paths that makes your performance metrics more robust, with a smaller variance, right? So that's the first disadvantage. The second disadvantage, which only applies to the expanding window, is basically the initial decisions are made on a smaller proportion of the data, right? So for example, here, whatever we are doing in the first fold, the decision is based on this train set, then next one, then next one. And as you can see, the initial decisions are based on a fewer observations. So we don't have this problem with the rolling window, but the problem with the rolling window is that these the folds are not necessarily large, right? So again, this is advantages and disadvantages of walkforward cross-validation, but this is one of those cross-validation techniques that it's most widely used, and it works. If time series is stationary, and this technique works just fine. And this is the one that comes with many Python packages like PyCaret, like scikit-learn, and etc. All right, the last one is called CPCV, Combinatorial Purge Cross-Validation. Okay, so this one is quite unique, especially when it comes to backtesting trading strategies, and it's very helpful because it gives us multiple backtest paths that span the entire data set. So what do I mean by that? So let me emphasize it one more time. The goal in CPCV is to generate multiple unique backtest paths that span the entire data set. Remember, in Purge cross-validation or in Walkforward cross-validation, we went through day 1 to day t, capital letter T, only once. That was basically your historical data. And especially when it comes to backtesting trading strategy, it can overfit. It can simply overfit. But the idea of combinatorial purge cross-validation is we're gonna do something like this. Imagine let's look at this one actually. I'm going to tell you what do we mean by S and what are the different things on the vertical axis. We call them group. So imagine you have, I don't know, 700 something observations, right? Let's call it 700 observation. And I'm going to divide it into 6 groups. So let's say group 1, 2, 3, 4, 5, 6. 6 groups that within these groups, we are not supposed to shuffle the data, right? So let's say you can think of these groups as months, right? So groups can be, in this example, months, right? So we don't want to shuffle the data within each month, right? And I have 6 groups here, so my G is equal to 6. And I want to test, so I want to keep 2 months of these 6 months as for my test set, right? For all these 700 observations, right? So let's say I want to test 2 groups or 2 months. So how many different ways can I do that? It's a combination of 2 of 6, right? So 2 of 6 is going to be basically 15 different ways, right? 6 multiplied 5 divided by 2. And so now this is where these S's are coming from, S1 through S15, right? So these are basically different splitting ways we can have if you have 6 groups that you don't want to shuffle them, and you want to for each cross-validation you want to use 2 of them as a test set, right? So we're going to end up with 15 different splitting methods, right? So now out of these 15 different splitting methods, we can come up, in this example, we can come up with 5 unique paths. So basically here, and let's go ahead and label them with numbers. So this is unique path that spans the entire data from, let's say, month 1 to month 6, day 0 to, I don't know, 700, the unit is different, right? So this is path number 1, path number 2, path number 3, number 4, number 5, and etc. Right? So again, there's a formula where we can get this number 5 here, but whatever it is, at the end of the day, using CPCV, now combinatorial purge cross-validation, we were able to generate, in this example, 5 unique paths that span the entire data set. So what's quite unique about this approach is that it will help us to avoid overfitting, and basically we don't get super optimistic performance metrics, right? So this is really, really important. So, and remember, in each path that we generated, in this example we had 5, we can look at the model's out of sample performance for the entire time period. All right, now let's move on to time series bootstrapping. As we discussed earlier, because there is this time dependencies in time series data, note IID bootstrapping is simply does not work because we cannot shuffle the data randomly. And so we know that the bootstrapping is random sampling with replacement. So if there's time dependency, we cannot do that. So what do we use for time series bootstrapping methods? There are 2 general types of bootstrapping methods for time series. One is parametric, the other one is non-parametric. Parametric ones are simply based on models, right? So we're going to work with models with IID residuals and resample from those residuals. So let's say, for example, we have an autoregressive model or a REMA model. We feed the data, and then we come up with the residuals. The residuals are going to be IID, and we're going to simulate back from those residuals, right? So we're going to simulate a synthetic time series from those residuals, right? And so this is a parametric approach. The second approach is non-parametric, right? So in non-parametric, we're going to call them block bootstrap, and it is where the data is directly resampled, right? So the underlying assumption is that these blocks can be sampled so that they are approximately IID. Yes, the data set, the time series itself is not IID, but we're going to put them in different blocks, and then we assume that those blocks are IID, right? So depending on how we define those blocks, we can come up with different non-parametric block bootstrap techniques, and we're going to cover 3 of them here. Moving block bootstrap, MBB, circular block bootstrap, CBB, and stationary bootstrap, SB. Okay, so the first one, moving block bootstrap, MBB. MBB samples overlapping fixed size blocks, and the size is M, of M consecutive observations, right? So the idea is that, so imagine this is our observed data, and we're dealing with overlapping fixed size. So this is one block, here's another block, you get the idea, different colors, right? So in this example, we're going to have 5 blocks with fixed size, whatever the size is. Then we're going to put them together, we call it resample blocks, and then we are going to sort them in a way that the length of the resampled blocks is the same as the length of the observational data, right? This is going to be our bootstrap data. And now we can repeat this process many, many times. We can generate many, many bootstrap observations, right? And just pay attention that the blocks indices starts from number 1 to number t minus m plus 1. So what does that mean? Imagine we have on the left hand side, we have 9 observations. 1, 2, 3, 4, 5, 6, 7, 8, 9, right? And imagine our m is equal to 3. The block size, the fixed block size that can be overlapping is 3, right? So this is block number 1, block number 2, and etc., right? So the index of the block bootstraps is going to start from index number 1. So here this is index number 1, and it goes all the way to index number capital letter T minus m plus 1. So RT is 9, M is 3 plus 1, so this is index 7. This is the start of the last block available in the data, right? So basically index 7. 1, 2, 3, 4, 5, 6, 7. So this is going to be our last block. And as you can see, maybe one thing that you may notice that the very last block is going to be the observations here are going to only be repeated once in this block, right? So maybe we should fix this problem, and this is exactly the motivation for circular block, right? The circular block assumes that the data lives in a circle, and now we can connect the first observation to the very last observation, and we can build more blocks on top of that. Then the very last observations are going to be repeatedly the same amount of time compared to the other part of the data observations. So here's the CBB, circular block bootstrap. As I said, it's a simple extension to the MBB, and which assumes that the data lives in a circle. So this is your T1, and it goes all the way to T capital letter T, last period, and then it goes back to T1 again. So this helps, first of all, it makes sure that your bootstrap has better finite sample properties because all the data points get sampled with equal probability. Remember, in moving block, let's say, in moving block bootstrap, the very last observations have fewer chance to show up in the data. But if I make it circular, then they're going to be repeated in a few forward blocks, and they have equal chance of showing up in the bootstrap. So this is the caveat of MBB, which is covered by CBB, circular block bootstrap. All right, the last one is a stationary bootstrap. So stationary bootstrap is, again, simply an extension to moving block bootstrap, but here the block size is no longer fixed. So if you remember, in our previous example, our block size was equal to 3. So we had the data and we came up with blocks of 3 observations. They could overlap, something like this. But now, in stationary bootstrap, we are going to choose an average block size of M. So we're going to say that on average, the block size is 3. So maybe I have a block of 2, and then I have a block of, I don't know, maybe without overlapping 4. And as you can see, the average is going to be 3. So the idea is that we can have different size blocks. And what makes it interesting is that if this stationary bootstrap is applied to stationary data, our resample pseudo time series. Remember, the bootstrap data, this is a synthetic time series, right? This new pseudo time series is going to be stationary. And this is very, very important because that's not the case for moving block bootstrap or circular block bootstrap. So in many cases, we transform the data, the time series data, to be stationary first. And then now, if you want to apply any kind of bootstrapping, the pseudo time series better be stationary, right? Because you want to, for example, you're applying some ARIMA models. ARIMA works under the assumption that the time series is stationary. And now if you want to look at the performance of the model in simulated data, your simulated data or synthetic data better be stationary, right? And I think one last thing I want to emphasize, that the popularity of stationary bootstrap is coming from the fact that it is hard to come up with the optimal value for a fixed block size of M, right? It's going to give you more room to just focus on the average value of that M, and then you can change the size of these blocks. It can be any number, right? All right, I think that's pretty much it. These are all the topics that I wanted to cover when it comes to time series machine learning and what are the challenges in time series machine learning. Okay, this wraps up the theory section of our module number 5. We did it in 3 parts, and now we are ready to go to the Python section. And as I said earlier, we're going to do it in 2 ways. We are going to use scikit-learn and model all the machine learnings for time series analysis from scratch. And then once we're confident with that and comfortable working with those models, we're going to move forward and work with PyCaret Python package. Until the next one, take care. If you're looking to stay updated with the latest versions of the course's materials, please make sure to follow my GitHub and remember to refresh your repositories periodically. If you find yourself needing a bit more background in econometrics, machine learning, or deep learning, check out my other YouTube videos for additional insights. And for all the latest news and quick updates, don't forget to follow me on Twitter. Thanks for joining me, and let's keep learning together.